All right. Well, thank you all for joining another lecture for interactive computer graphics. Okay. Today's topic is going to be, remember those raster images we talked about? Today's topic is going to be about how to generate those raster images. That is, the rendering algorithms. Right? We're going to talk about how to generate those. Now, the slide deck that I'm going to be using for today's lecture is going to be the same, well, almost, not exactly, but almost the same slide deck that I used for teaching exactly this topic when I was teaching Introduction to Computer Graphics. So those of you who have taken Introduction to Computer Graphics from me, this lecture is going to be somewhat of a repeat. So yeah, as I said, there's going to be some overlap between these two courses, and this is one of them. This is one of those lectures. But towards the end, maybe there's going to be a few different things. All right, let's start our topic. Rendering algorithms. So what are we trying to do with rendering algorithms? So the goal is that I have this screen, and I would like to create some image on this screen, right? An image of some virtual object. Let's say Utah Teapot. Why not? Let's say I want to create an image like this. So the main problem that the rendering algorithms are going to be solving is what we call the visibility problem. That is, I have this teapot in a virtual environment, and where does this teapot fall on my screen here, right? Basically this, right? Like, where is the teapot on the screen? So the primary problem, not the only problem, but the primary problem that these rendering algorithms are going to try to solve is this visibility problem. Well, like, where is this object, and what part of the object falls on what pixels, right? So, and then from there, we can go on to coloring those pixels accordingly and generating an image like this, right? Broadly speaking, when we look at rendering algorithms, we can classify them into two groups: rasterization-based algorithms and ray tracing-based algorithms. And we're going to talk about both of them. So in rasterization-based algorithms, there are a number of them. Probably the simplest one is the Painter's algorithm. So we're going to start talking about the Painter's algorithm first. The most popular rasterization-based algorithm, possibly the most commonly used algorithm in the world, is Z-buffer rasterization, because that's what our GPUs do. And we're going to talk about that quite a bit. And then we'll also talk about briefly this A-buffer and Reyes are different, more advanced offline rendering algorithms using rasterization. I will also talk about ray tracing. Ray tracing can be thought about like the fundamental algorithm that allows you to implement rendering algorithms such as ray casting and path tracing. We're going to briefly touch on those, but I'm going to give an overview of how ray tracing works, right? So that's going to be our main topic for today. So let's start with rasterization. So the problem that rasterization tries to solve is this. Remember last time we talked about transformations? We took our objects from model space, we went to world space. From world space, we went to camera space. From camera space, we went to canonical view volume. Let's say that we did all that, and our object, in this case, just one triangle, is living in this canonical view volume now. So we know where the triangle is in the canonical view volume. The nice thing about this canonical view volume is it's a 3D volume, right? There's some depth to it. But what we see is just the 2D part of it. So there's an X, this is the X coordinate, and this is the Y coordinate, and Z coordinate is towards you in the canonical view volume. If you collapse the Z coordinate, you get an image like this. If you rasterize that image, that is, if you convert it into a bunch of pixels, it will look like this. So this is going to be the raster image that's coming out of this canonical view volume. And the problem of the rasterization algorithms will try to do this conversion, go from canonical view volume to a raster image, right? So it's going to be sort of pixelated because a raster image is made out of pixels. All good? All right. Of course, it doesn't have to be pixelated that badly. So we could sort of smooth the edges a little bit. This is the process that we called anti-aliasing. I'm not going to get into too much detail. I'll talk about it a little bit today. But I don't want to go into details of describing what anti-aliasing is and where it comes from. But this smooth edges, you can think of them as like when you put this triangle onto this raster image, these pixels are colored based on the proportion of which this triangle covers those pixels. So the portion of the triangle that is covered, the portion of the pixel area that's covered by the triangle will be colored by the color of the triangle, and the rest of the pixel is going to take its color from the background, and the combined pixel color is going to be just one color, right? The combined pixel color is going to be a mixture of the triangle color and the background color, which is white in this case. All right, so this is what an anti-alias image would look like. Of course, when your pixels are this big, it kind of looks funny. But when your pixels are actually the size of a pixel, an anti-alias image looks really nice, and it doesn't look jaggedy like an alias image. All right, so this is all good. The problem with rasterization, one of the fundamental problems with rasterization is going to be what to do when you have more than one triangle to deal with. So if I have another triangle here, in this case, this triangle is in front of the other one. Like, how would I handle this? First of all, I need to figure out where that other triangle is. Is it in front of the red one, or is it behind the red one? I kind of need to figure it out, and based on that, I'm going to be generating the image. All right. So let's start talking about the painter's algorithm first. All right. So the painter's algorithm will imitate the process with which painters would generate an image, right? So let's say that I have this canvas, and I'm going to build I'm going to paint something on it, right? So this is my canvas. I can start with a background, right? So this is the sky. I painted the sky, and then maybe there was some ocean. Maybe there's some clouds in front of it. Well, then an island in the background. Some other terrain, and something in front of that, and something in front of that. You see what we're doing? We're going from all the way from the far distance, and we're trying to come closer and closer to the camera, closer and closer to you. And something in front of this, and something in front of that, and something in front of this, and something in front of that. All right, and what comes in front of this? The great Bob Ross, of course. All right. So this is how the painter's algorithm would work. Now let's put this in the context of computer graphics. How does that work? Well, let's say I have this very simple scene, and I'm going to generate an image with this very simple scene. In this scene, I have two triangles. Fairly simple scene, I would say. So the painter's algorithm will begin with sorting these triangles, sorting them from back to front based on their distance from the camera. And we're going to follow the painter's algorithm and draw things at the far end first. That is, we will first draw the blue triangle. And we know where the blue triangle is in the canonical view volume, so we can tell where it lands on the screen. And we can paint those pixels that correspond to that triangle area, right? And after that, we're going to take the red triangle, and we're going to paint it on top of the previous one. And this is how we generate an image using the painter's algorithm. This is all good. Of course, the problem is the same problem that the painters face. That is, you paint something and then you paint over it, right? So it kind of looks like wasted computation, but at least you generate a proper image. Well, you generate a proper image, that is, if your triangles are not intersecting. Yeah. So if your triangles are intersecting, this becomes a little bit tricky. Because can you tell me which triangle is in front of the other now? Now, if I were to sort it, it's kind of tricky, right? Is the blue one in the back or the blue one in the front? You think maybe? I mean, I can generate this or the other one, right? There's nothing in between. I can either draw the red one first or the blue one first, and the painter's algorithm will give me either this image or this image. But it will never give me this, which is what I'm supposed to see. Right? So with painter's algorithm, I always get something like this, which is not so ideal. Yeah. So that's the problem with the painter's algorithm. So you might say, oh, where would I ever have this problem? Okay, you just picked two triangles that were intersecting with each other. Do you even get models like that to render when you're dealing with realistic, more general computer graphics today? Well, I can give you an example model where this happens. Can you think of one? I think there's one you can think of. The Utah teapot. Right? Utah teapot actually has triangles that are intersecting with each other. So you cannot properly render Utah teapot using painter's algorithm. It won't be able to do that. All right, so the painter's algorithm is going to have some trouble with this a model that has intersecting triangles. Yeah, that's going to be a problem because it needs sorting. Now, sorting is sort of expensive. It needs to handle that, and to be able to sort things, we need to make sure that the triangles are not intersecting. Otherwise, we can't really sort them based on the distance they have from the camera. So that's the problem with the painter's algorithm. That's one of the major problems with the painter's algorithm. So moving on to solving this problem is going to be the most popular algorithm in the world. That's going to be the Z-buffer rasterization. And this is the most popular algorithm in the world for rendering because that's what our GPUs are designed to do. Now, this is a graphics card, not a GPU. The GPU is the chip inside this graphics card. But you get the idea. So this is the Z-buffer rasterization is the algorithms that our GPUs are designed to use for rendering. And here's how it works. Again, it's a rasterization-based algorithm, so it's going to take triangles in the canonical V-volume, and it's going to generate a raster image like this. The problem it solves is the visibility problem that the painter's algorithm could not solve. The way that it solves that problem is by storing, along with the color that is RGBA, by storing a depth value for each pixel. So each pixel will also store how far that point is, that pixel is from the camera. That is, more specifically, at the center of the pixel, how far that point that corresponds to the center of the pixel on that triangle is from the camera. All right, so that's what Z-buffer rasterization does. Remember, pixels are not little squares. Now I'm drawing them as little squares here just to visually give you what it would look like if you were to enlarge your displays. But pixels are actually samples at the centers of these pixels, right? So at the center of a pixel, I'm going to have the color value and a depth value, depth meaning how far it is from the camera. So remember our canonical V-volume? So this is going to be the X direction. This is going to be the Y direction. This is the Z direction, right? So we don't call it RGBA depth. We sometimes call it, instead of depth, we call it Z. Now that's why it's Z-buffer, right? So basically, this is going to store the Z value, the Z coordinate for every pixel. I mean, we already know it's the pixel's X coordinate and its Y coordinate. We're going to store the Z coordinate of each pixel here together with the color for the pixel. And with that, we will be able to handle the visibility problem. So if I have another triangle here, if I just put another triangle in the scene, Z-buffer rasterization will be able to figure out for each pixel which triangle is visible. So if this blue triangle is behind the red triangle, when I render it, I'll get an image that looks like this. If they're intersecting with each other, like in this case, then it will figure out for each pixel which triangle is in front. Right? So in a way, it is able to sort the triangles per pixel, because it's not actually sorting the triangles. It's just comparing the Z coordinates whenever you draw a triangle and figure out where that triangle lands on this raster image is figuring out the z coordinate for each pixel as well. And with that z coordinate, it can tell which triangle is in front. The triangle I drew before, that is in the z buffer, or the triangle that I'm drawing now. Okay, for each pixel, it will figure that out. And with that, it's able to solve this problem of triangles intersecting with each other. That's the primary reason why, well, one of the primary reasons why we use z-buffer rasterization as opposed to the painter's algorithm. Yeah, it's a very, very old algorithm, and it's still the most commonly used algorithm in the world today. Now, okay, this is nice and all, but it's looking kind of jaggedy, right, with the pixelated. What if I wanted to have anti-aliasing, right? What if I want to have these nice smooth edges? What would happen then? Can rasterization handle that? Yes, it can handle that as well. So basically in this case, just like the case I showed you before, here for these pixels, the color is coming from the color of the triangle and the color of the background. Like we're blending them based on how much the triangle is covering that pixel. For the pixels where the two triangles overlap, the color is coming from either the blue triangle or the red triangle or the background, if there's background visible there as well. So it's going to be a mixture of all of them. So this is what the z-buffer rasterization is able to solve by storing multiple samples per pixel. So for each pixel, if I store multiple color values and multiple depth values, I can do anti-aliasing. So this is what we call super sample anti-aliasing, SSAA. The super sample anti-aliasing with 4x will store 4 samples per pixel. You may think that this is like an overkill, and in some ways it is. You know, I'm now storing 4 times as much data as I would store otherwise, and I'm generating 4 times as much data. Yeah, so this is sort of expensive, but at least you get these nice looking smooth edges with it, right? So as opposed to storing a single sample like this, where you would get these jaggedy edges, with SSAA, you would get smooth looking edges. Of course, you can store more than 4. 4 is not great. An ideal number that is preferred is about around 64. 64 gives you very good, nice anti-aliasing. For interactive rendering, it's a little too expensive though, but 4x is something we are able to do. Well, we can do something a little better with z-buffer rasterization. We can sort of simplify this. Now, remember, for visibility, what's important is the depth, the z value, right? That's what we're trying to compute in multiple places on a pixel. So instead of doing this, like, you know, storing color plus depth in 4 different places with 4x anti-aliasing, instead, I could use what we call multi-sample anti-aliasing, in which case I'm storing 4 depth values, but only 1 color value. So for each pixel, I'm going to store a single color. That's going to be the combined color of everything, but I'm going to be storing multiple depth values, right? And by doing so, I can figure out which triangle to choose for which sample of a pixel, right? And I can generate nice looking anti-aliased images, right? Of course, so this is what you would get with without any anti-aliasing. And this is, you know, when you have 4x anti-aliasing, you get these nice smooth looking edges. All right, going back. Anti-aliasing. Yes, anti-aliasing problem can be solved with z-buffer rasterization without any problems. It works just fine. Of course, you know, there's some cost to it, cost associated with it, but you can handle it. And our GPUs, actually, implementing z-buffer rasterization, are able to do super sample anti-aliasing or multi-sample anti-aliasing. So our topic today is not anti-aliasing, so I'm not going to get into other types of anti-aliasing today, but there are other anti-aliasing techniques that are supported by our GPUs today. But those are the basic anti-aliasing techniques that are used in z-buffer rasterization. Now, z-buffer rasterization, however, is not perfect. It struggles with semi-transparent objects, semi-transparent triangles. So if the 2 triangles are opaque, z-buffer rasterization is fine. But if one of my triangles, let's say the red one in this case, is semi-transparent, you know, this would be the image that I would like to get, and I can get it only if I render the triangles in the correct order. So if I render the triangles at the back first, the blue one, and then I render the red triangle that is semi-transparent, I will get this image with Z-buffer rasterization. For that, our GPUs are able to do alpha blending. Now, here's another keyword. If you're not familiar with alpha blending, please do look it up. GPUs are able to do alpha blending for handling transparency, and they can produce an image like this. If I draw them in that order, that is, I draw the blue one first, and on top of that, I draw the semi-transparent red triangle. But if I do the opposite, if I draw the semi-transparent red triangle, it's looking sort of a lighter shade of red because background is visible. If I draw this one first, and then I draw the blue one, what happened? Now I'm not getting what I was supposed to get. I was supposed to get this, but I'm not getting that. Instead, I'm getting this, right? So that's not great. And the reason why this is happening is that with Z-buffer, I have one Z value. And when I draw that red triangle, the red triangle wrote the Z values for each pixel. And now when I'm rendering the blue triangle is going to compare its Z values with the Z values of the red triangle, and Z-buffer rasterization will say that, oh, this triangle is behind the other one. Yes, but that the triangle in front was semi-transparent. This is supposed to go behind it. Well, it's a little too hard to handle for Z-buffer rasterization. So you won't be able to produce an image like this if you don't render the triangles in the correct order. So Z-buffer rasterization can handle intersecting geometry, and it does not require sorting the triangles before you render them, but it will require sorting the triangles when you have transparency. Right? When you have transparent triangles, you will need to render those transparent triangles after you render the opaque triangles. So that's actually how a lot of game engines work. When they have transparent objects, they would be rendered much later. So you first render the opaque stuff in your scene. After you're done with your opaque stuff, you render the semi-transparent objects on top of them. So if you like glass windows and things like that, they're rendered after you render the opaque objects. And also, you kind of need to have sorting. You kind of need to render them in the correct order, especially if you have one semi-transparent object in front of another semi-transparent object. You need to render them from back to front. Otherwise, you won't get the correct result. Right? So that's the limitation of Z-buffer rasterization. But that's what we have on the GPU. So that's what we're going to have to deal with. So we're going to have to be careful when we're rendering semi-transparent objects. Now, this is not a fundamental limitation of rasterization broadly. There are rasterization algorithms that can handle things like this. For example, A-buffer rasterization is another rasterization algorithm that can handle these type of situations where you have semi-transparent objects and you're not able to render them in the correct order. A-buffer rasterization as a different rasterization-based algorithm can handle this. But it requires more and dynamic memory allocation. That's why our GPUs are not designed to use A-buffer rasterization. Now here's how it works. With A-buffer rasterization, I don't just store a single depth and color value. For each pixel, I'm going to store a list of what we call fragments of these triangles. A list of fragments for each pixel that will contain everything that's visible through that pixel. So this is the backgrounds, in this case, and it's the blue triangle and the red triangle. And for the pixel in the middle here, I have a list of all of them. And together with their depth and RGBA values, I also have a coverage mask. So I know what part of that pixel they're covering. And by doing this, I can figure out which triangle is in front of which other triangle, regardless of what order they come in. So if I end up rendering the red triangle first, and then let's say I'm going to draw the blue triangle, when the fragments of the blue triangle come in to that pixel, I can just place them in the middle here inside that linked list. So doing this A buffer rasterization is able to handle semi-transparent objects without any problem. Now, some forms of A buffer rasterization can be implemented on modern GPUs, but that will require some custom code that you're going to have to write, and you're going to have to handle this, linked list and all that on your own. The GPU itself is not designed to do A buffer rasterization. We can do some forms of A buffer rasterization on the GPU. It is definitely possible to implement A buffer rasterization on the GPU on top of its Z buffer rasterization, but GPUs don't do that by default. It will require you to write some code to handle this sort of linked list manipulation here, right? So this is not the algorithm that GPUs use, even though it can be implemented on the GPU. Another rasterization-based algorithm, very widely used, was REYES, that is called Render Everything You Ever Saw. It's short for that. So this is the algorithm that Pixar used for many, many years, for pretty much all of its movies, up until recently. REYES was the fundamental algorithm of RenderMan, Pixar's renderer. And here's how it works. It's a rasterization-based algorithm. What it does is that when you have an object like this, let's say it's a sphere, what it does, it just takes every piece of that sphere and splits it into smaller and smaller and smaller pieces, right? Such that each one of these pieces become smaller than a pixel. And when they're smaller than a pixel, you get the detail that you want, right? So that's the goal of this REYES algorithm. So it takes a surface like this, and it splits it and splits it and splits it into these what's called micropolygons, and then figures out where those micropolygons are in screen space. Also figures out where the pixels are in texture space. We're going to talk about texture mapping and all that much later. So if this image doesn't make too much sense, don't worry about it. But basically, it's instead of rendering triangles as big triangles, it's just splitting them into smaller and smaller and smaller pieces so that you can get lots of detail in it. And so of course, this is not designed for interactive real-time rendering, so GPUs don't implement something like this. But with REYES, you can get really high-quality, super detailed images like this. So this is an image rendered using RenderMan. I believe it's using REYES. I might be wrong, but I believe it is using REYES. Here's another example, just some examples of offline rendered images, not interactive, not real time, so not a part of this course. Let's move on. All right, let's move on to ray tracing. Is ray tracing interactive? Well, it can be, but let's talk about the concept of ray tracing first. So I'm going to talk about ray tracing by comparing it to rasterization. Now, for rasterization, all of the rasterization algorithms basically implement this loop. Like for each primitive, for each triangle, I'm going to take that triangle and put it on screen space and figure out what part of the screen that triangle corresponds to. That is, for each primitive, find the pixel samples that correspond to that triangle, correspond to that primitive. You take each primitive one by one, and then you place them on the screen, and that's how rasterization works. All of the rasterization algorithms work, but basically implement this loop. So, and they differ based on how they handle primitives and how they handle what they do once they figure out what these pixel samples are, right? With Painter's algorithm, you just put the color of that triangle for that pixel sample. For Z-buffer rasterization, you check if the previous color was coming from a triangle that was closer to the camera. For A buffer, you put it in a linked list, right? So all these algorithms differ by what they do after they figure this out, but they execute the same loop. Ray tracing is going to execute the opposite loop, the inverse loop. That is, for each pixel sample, we're going to start with pixel samples. For each pixel sample, it will find the closest primitive that corresponds to that pixel sample. Right? It's going to do the opposite loop. So you can really think of ray tracing is like the doing the same thing in an opposite way. Right? The goal is still generating this raster image, right? But rasterization starts from triangles and goes to the raster image. Ray tracing starts with the raster image and goes to the triangles. to do the same thing. All right. So in 3D, if I were to render an image, let's say in this scene, like there's my camera, this is what I see. Looking into my scene, and here's a triangle. With rasterization, I will take that triangle and figure out where it lands on the screen. That's where it is. Take the next triangle. I'm going to figure out where it lands on the screen. And I'm going to draw it like this. So as we talked about, different rasterization algorithms can handle different things. With Z-buffer rasterization, if these two triangles are intersecting with each other, we can easily handle that. But that's how rasterization works, right? Triangle, move them to the screen. Triangle, move it to the screen, and figure out where it falls on the screen. With ray tracing, as I said, we're going to start with the raster image. But first, we're going to start with the raster image, and we're going to figure out where each pixel sample corresponds to in the scene. So we must have a representation of the entire scene before we can do anything. So for ray tracing, we will have all of the scene given to us first, right? This is my entire scene made out of two triangles. And it supports different types of camera models, so we don't have to have projection matrix and all that. It's actually really general in that sense. So what I'm going to have to do is that for each pixel sample on the screen, I'm going to be generating an array starting from my 3D camera position, going through that pixel sample, and I'm going to trace that array until I find an intersection with a scene primitive, in this case a triangle, right? And once I find that triangle, I found that, I hit that triangle exactly at that point, I am going to color this pixel based on the color of that triangle. So what happens if I have a semi-transparent triangle like this? Fairly easy. I've traced this ray and found that hit. You know what? I'm just going to continue. I'm going to continue tracing that ray and find the next hit. If it's an opaque triangle, now, okay, I found the two triangles I need for that pixel. And I can color them accordingly, color the pixel sample accordingly. If this is also a semi-transparent triangle, I can continue. So ray tracing can handle semi-transparent triangles, and also, you can handle them in various different orders, so you don't have to order them at all, right? So that's basically how it works. And to be able to generate a full image, I'm just going to have to generate rays and trace them for every pixel sample. And once I do that, I'm going to have my final rendered image, right? So this is how ray tracing works. Now, okay, I mean, it's doing the same thing. Maybe it's a little bit better in handling semi-transparent triangles. But other than that, it doesn't look... Why would I pick ray tracing over rasterization? It's just, an alternative. Okay, it's a little bit better maybe because it can handle semi-transparent objects. What makes ray tracing much superior as compared to rasterization is that it can do more beyond just finding what pixel corresponds to what triangle. It can do a lot more. Here's what I mean. Now, let's say that I'm trying to render a scene like this, okay? I'm going to pick a pixel here, and I'm going to pixel sample. I'm going to generate a ray, and I'm going to trace that ray, and this ray is what I call a primary ray from the camera that's passing through a pixel sample on the screen, all right? And I trace that ray, and I find the intersection point. All right, so all good. This is the primary problem that we're trying to solve in rendering, and it's able to solve that. It's very good. This is what we call ray casting. Now, after that, I can still use ray tracing to do other things. For example, if this surface over here, this surface over here, turns out to be a shiny surface where I see some mirror-like reflections on it, ray tracing is able to solve those reflections for me. So if I'm looking at a reflective surface like this from this direction, what would I see on that reflective surface? I can find out by reflecting this ray on that surface, right? So I reflect that ray where it hits that surface, and then I continue tracing. And this is what we call a secondary ray. So the primary ray is generated from the camera, a secondary ray is generated on the surface. And by tracing that secondary ray and finding that point, I can actually render images that contain proper reflections like this. And that's very, very easy to handle in ray tracing. All sorts of reflections, all sorts of different types of secondary rays are very, very easy to handle in ray tracing because they use exactly the same ray tracing algorithm. So from the perspective of ray tracing, there is no difference between a primary ray and a secondary ray. It's just a ray. And all it does is, figures out what triangle you hit with that ray. So I can use exactly the same algorithm for solving more general problems than just the primary visibility problem that rasterization algorithms are able to handle. So with ray tracing, it opens up these possibilities of different types of things that we could easily compute by using secondary rays. And secondary rays are used for computing reflections, refractions if you have a transparent object, shadows, and realistic illumination with bounces. We're going to talk about realistic illumination quite a bit, so I'm going to skip that and just say that involves computing reflections in different ways. So ray tracing is able to handle that, and because of that, you can use ray tracing to generate really, really realistic images. Right. So comparing ray tracing and rasterization again. Now, rasterization, more specifically Z-buffer rasterization, I told you, is the most popular rendering algorithm. But it is the most popular rendering algorithm only because that's what our GPUs use. And there's a reason for that, which I will explain in a minute. But if you're going for highly realistic offline rendering, then your choice is definitely ray tracing, because this opens up possibilities for computing really, really realistic images, which is going to be very, very hard to do, or in some cases impossible to do with rasterization. Right? But why don't we design our GPUs for ray tracing, not for rasterization? Okay, I'm hearing some of you think that, hey, new GPUs support ray tracing. Ray tracing support is something else. They are still designed for rasterization. They do a little bit of ray tracing, but they are designed for rasterization still. And there's a good reason for that, because this operation, find pixel samples, is super fast. But find the corresponding primitive for an array is super slow. Right? Now, this is super fast. I have a triangle. I've drawn it on the screen. Where are my pixel samples? Super fast to find. But I have an array. I have millions of triangles in my scene. Which triangle do I hit? That's super slow. All right? That's very hard to find. Moreover, this process of for each primitive, that means I'm going from one primitive to the next primitive to the next primitive to the next primitive. Guess what? If I'm going to go over my scene by rendering one triangle after another triangle after another triangle, I'm going to have very, very predictable memory accesses, right? And memory can be very, very slow in modern hardware. So by accessing the memory linearly, this linear access makes rasterization super efficient in the way that it's accessing the scene data. Like I am taking one triangle after another triangle and another triangle and another triangle. Of course, with GPU parallelization, I'm pretty sure you all are familiar with that concept of GPU parallelization. We're not rendering one triangle after another triangle. We're rendering a bunch of triangles all at the same time. But we go over our scene data from start to end, right? So we're streaming the whole scene data from start to end into our GPU, and our GPU is able to render it using rasterization. With ray tracing, however, I have my pixel samples, I have my rays, and then I need to figure out which triangle those rays would hit. Yeah. So, I'm not looking at those triangles in order. I could, in theory, for each ray, go over the entire scene, but that would be super slow. So what ray tracing algorithms do to accelerate that is, instead of looking at each triangle for each ray, they will take the scene data and split it into spatial partitioning structures so that they will be able to very quickly find the possible triangles that can intersect with that ray. But doing that, though it accelerates this, super slow, find the closest primitive stuff, it's still slow, but makes it faster. It ends up being like a search operation in this scene database, right? I have the scene database of all these triangles, and ray tracing is effectively doing sort of like a random search, right? It's going to try to figure out where each ray is. So it's going to be accessing the scene data rather randomly. So this random memory accesses, well, that makes the data flow really inefficient as well. So that's another problem with ray tracing. But if you were to think about this theoretically, when you think about number of triangles in the scene, rasterization has linear complexity. That is, if I have a million triangles, I'm going to be drawing a million triangles, right? I start from the first triangle, I go all the way to the end of the list. I go over my list once. That will be linear complexity in terms of the number of triangles. But with ray tracing, I'm doing a search operation. So I might have a billion triangles in my scene, but maybe my camera is placed such that I'm not accessing all of that. And for each search operation here with this complicated spatial partitioning structures, like BVH, we can accelerate this, and also we don't have to access all of the scene linearly. So we can get sublinear performance. In theory, actually, we can get logarithmic complexity in terms of the number of triangles we have in the scene. So when you think about this, if you're rendering a very, very, very large scene, lots and lots of triangles, you would expect ray tracing to be still faster than rasterization, right? Because, I'm pretty sure you all are familiar with the complexity theory, right? So if you have an algorithm that has linear complexity compared to an algorithm that has logarithmic complexity, you would expect that algorithm with logarithmic complexity to get faster at some point. There's a constant factor, of course. You don't know how large your scene is supposed to be for ray tracing to be faster than rasterization, but you would expect it to be faster than rasterization at some point. You would expect that. Turns out in practice, there's also this issue. Random memory accesses and linear memory accesses. So when you have a very, very large scene, this becomes very, very, very bad. And this becomes much, much better. So even in large scenes, ray tracing struggles to catch up with rasterization because memory accesses become a big problem in that case. So this logarithmic complexity, in theory, is not helping us so much. Nonetheless, with rasterization, you can only handle primary visibility. All right, so take all of your triangles. Where do they land on the screen? That's all you can compute, and then you're done. With ray tracing, we can do a lot more than that. And by doing a lot more, we can generate really realistic looking images like this one. Well, because this guy is not rendered, but the background is. And here's another scene. Like you look at these and they're like real, right? This is a rendered image, but it doesn't look like a rendered image at all. It looks like a photograph in many ways, because by handling secondary rays, we can actually solve this rendering problem really realistically and generate images that are very, very difficult, in some cases impossible to generate using rasterization. So that brings another thing, like why not do ray tracing plus rasterization? So we can handle primary visibility using rasterization, which is fast, and then we can handle secondary effects like reflections, refractions, shadows, and realistic illumination, all that stuff. We can handle that using ray tracing, right? Does that make sense? We use the fastest method for rasterization, and then we use ray tracing to do all the rest. This is a great idea. Actually, this is a very popular thing today, because that's what our GPUs are capable of doing. Now, as I said, our GPUs with ray tracing support are still designed for rasterization because they want to handle the primary visibility using rasterization because rasterization is really, really, really fast as compared to ray tracing. And they can do a little bit of ray tracing on top. So they can do some reflections, refractions, and shadows, and some realistic illumination stuff. So they can do a little bit of this stuff. So they are actually pretty good for mixed ray tracing rasterization type of rendering. And so that's very good. This is not what people use for offline rendering though. Offline rendering like for visual effects and movies and things like that. When you're not doing interactive rendering, we don't need rasterization at all. And the reason why we don't need rasterization at all is that, we could have mixed rasterization ray tracing, but ray tracing is able to handle this, the primary visibility too. So if I have a ray tracer that can handle this, why do I need rasterization? I don't need it. Okay, I don't need it, but rasterization is faster, right? Guess what? It doesn't really matter. Because for offline rendering, for generating those really super realistic images, this part, this ray tracing part for secondary rays, the secondary effects, that's where you spend most of your rendering time. Almost all of your rendering time goes to this. And for this part, yes, ray tracing is slower, but this part is still, regardless of you use ray tracing or rasterization, this part is so much faster than this part. So if I have a ray tracer, I might as well use it for primary visibility as well and be done with it. All right, I don't need rasterization. And there's actually something good about that because rasterization becomes getting slower and slower when you have larger and larger scenes. Handling really complex scenes becomes a little bit of a problem with rasterization. So rasterization has its own limitations. So by not using rasterization at all, you get rid of all of those limitations and you have ray tracing based renderer. You don't worry about the limitations of rasterization. Everything works just fine. So that's what people use for offline rendering. But this course is interactive computer graphics course. That means we're going to mostly concentrate on how to do interactive rendering. So in the context of interactive rendering, this is still a very, very, very good idea. All right. We definitely want to handle primary visibility using rasterization because that's what our GPUs are designed to do. That's what the GPU rendering pipeline is designed to do. And we can do ray tracing if our GPU has ray tracing support. We can do a little bit of ray tracing on top of that for handling these secondary effects. So this is the most modern way of looking at interactive rendering today, right? This mixed rasterization ray tracing. Actually, this is how offline rendering worked like about 20 years ago. But today, they sort of ditched rasterization completely and everything is based on ray tracing. And today, in the last couple of years, we started having ray tracing support in our GPUs, so we can do this mixed ray tracing rasterization type of renders today. And my hope is that in the future, I don't know, 10, 20 years from now, maybe not that much, maybe even longer than that, we'll see. We will ditch rasterization for interactive computer graphics as well, and everything will be based on ray tracing. So that's my hope, but we'll see how long it will take for us to get there. So we still need to have faster ray tracing support for GPUs to accomplish that. Nonetheless, some of these effects, reflections, refractions, and shadows and all that stuff, it's not like we don't have reflections and refractions or we don't have shadows in interactive renderings, right? You guys must have played some video games or at least have seen some video games. You must have seen some shadows in video games. Well, I don't know, maybe 5 years ago where there was no ray tracing support, we could still get shadows. We could still get reflections like this, right? So check this out. This is what I'm able to generate inside PowerPoint. PowerPoint is not using ray tracing. How am I able to do this? I do that using rasterization. This is a total trick, but it works. So in some cases, you can actually get all these secondary effects using rasterization and rasterization only. uh, in this course, we will actually talk about how to do rendering with rasterization, and we will talk about how to do effects like this one, all sorts of complicated things like this using rasterization. And it is definitely possible to do. Now, if you guys are wondering how I did this, it's kind of like a magic trick. When you show how it's done, it's not that impressive. But let me go ahead and show you how it's done, because we're going to talk about stuff like this. So in this case, to be able to get this, what do? You just render the teapot twice, like this. I'm rendering actually 2 teapots. One at the top, one at the bottom.
And when I put the plane back in the middle, this is what it looks like. My reflection rendering
is this. So, there are things we can do in the context of interactive computer graphics using rasterization to be able to get those secondary effects and nice looking images without using ray tracing. In this course, we're gonna talk about all sorts of different applications of rasterization for getting effects like reflections and shadows and other things. All right, but I am not going to get into them today because I don't want to get ahead of the other topics. So for today, this is where I'm going to end. So let's talk about what comes next. So next week on Tuesday, we're gonna have our first project, and starting with next week, we're gonna have a project deadline every week. So just to be clear, project deadline is next week. So the project is announced. It's on the web page. You'll see that this is what I call a Hello World project. So this is very, very simple. We're going to be just opening up a window for OpenGL, and that's about it, pretty much. There's a little bit more than that. The goal here is to just get things started. We're going to be using C++ and OpenGL for the projects in this course, and OpenGL is a platform-independent graphics library, so it works on any platform. But to be able to get it working, you need to create a window and stuff, and that is platform dependent. So there are platform independent libraries, and that's the one that I'm going to be recommending. So we're going to talk about how to do all that stuff next time. Our topic is going to be about how to handle user interrupts and how to generate a window and how to start rendering into that window. We're not going to render much just yet. The first project is going to be much simpler than that. But we're going to talk about the content that's related to the next project, how to handle Windows, not the Windows operating system, but opening up a window where you can display an interactive OpenGL rendered images. All right, until then, stay safe.